In one of the questions from Quiz 0, I asked you state the number of unpaired electrons in several different chemical species, some neutral, some cations, some anions, and is that species diamagnetic or paramagnetic? Obviously, you need to know what those terms mean. Carbon and zinc, I just picked two from the quiz, there are others. The first thing you should be reaching for, of course, is your periodic table, unless, of course, you have it memorized. And what am I going to do? Well, the first thing I'm going to do is I'm going to write the electron configuration of both of these species. Carbon, 1s2, 2s2, 2p, and how do you get that? Well, boron is 2p1, carbon is 2p2, right? So now we have the electron configuration, but does that give me the answer? Yes and no. If you know what this means, obviously yes. But if you forget what does this 2p actually represent, then you might be in a little bit more of a problem. What you have to remember is this 2p is actually representing the 2px, 2py, 2pz orbitals. How do we put the electrons in? Well, the p orbitals, the 2p orbitals, are degenerate. That means that they're at the same energy level. So I have two electrons. Well, this is why I keep harping on you've got to go back and review your quantum mechanics. There are rules that govern how electrons go into degenerate orbitals. Hund's rule. What we're going to do is we're going to place the electrons in a way to maximize spin. The first, actually let me use a different color. If I put the first electron into the 2px as spin up, I can put the next one in y or z. It really doesn't matter. I'll just go with y. But it also must be spin up. We have to maximize spin. Now you might say, well, why not just pair them? Wouldn't that make a lot more sense? Just have those two electrons paired up and everybody's happy? But they're not happy. Fundamentally, an electron has a negative charge. So another electron, well, it also has a negative charge. What happens when you have two particles with the same charge? They repel, right? If I have two magnets and if I point them together with the North Pole, they don't like that, they repel. If I flip it over and bring them in, that's going to be the South Pole. Well, in this case, yes, I could pair them, but that's actually higher energy because the electrons want to repel each other, right? They repel each other. So instead, what is observed is that each electron goes into a different orbital and it maximizes spin. Therefore, carbon has two unpaired electrons. By definition, if you have one or more unpaired electrons, then you're paramagnetic. So this is paramagnetic. Diamagnetic means that we have zero unpaired electrons. For zinc, now I'm going, again, I could start 1s2, 2s2, and so forth, but if we recall, well, so here is zinc, so using the noble gas configuration, argon core. So we have zinc with an argon core, but how do we put the rest of the electrons in? We have the 3D filling as well as potassium and calcium, which are the 4s. By convention, now again, your textbook actually does it kind of the opposite of how I learned it, but I'm going to put it this way. We put the lower quantum number first. So it's 3d10. 4s2. And if you reverse it, Again, it's one of those things where I'll probably teach it the way the book does it. You get the same result. Now, is this diamagnetic or paramagnetic? Well, I could draw out the diagram for both of these orbitals, the 3d and the 4s2, just as I did for the 2p, but I don't need to. And the reason why is the d subshell can hold a total of 10 electrons. It has 10. So it's full. Therefore, it must be diamagnetic. The 4s2, well, the s can only hold 2 electrons, and it's full. Therefore, this must be diamagnetic. And 0 unpaired electrons, right? So again, here, I didn't write it down, but by inspection, you can see it's 2, and here, it's 0 unpaired electrons. By all means, you can go ahead and write this out. We will be doing this quite a bit, where you put all 5 d orbitals and then you fill them up, but you don't need to. What about our argon core? Well, of course, the whole point of the noble gas configuration in nomenclature is to show that this is completely full. Therefore, it's diamagnetic. It's not going to have any contribution to paramagnetism. Diamagnetic versus paramagnetic is going to be a very, very, very recurring theme in inorganic chemistry, because these D block elements very often will make complexes that have unpaired electrons, 1 or more unpaired electrons. In fact, that's something that we'll look at with electron configurations with the D block, of how certain complexes, their magnetic and optical properties are going to dramatically change whether they're diamagnetic or paramagnetic. So again, that's kind of foreshadowing in the future. So it is critical to be able to write these electron configurations and then understand what they mean from an electronic point of view. And the reason I chose carbon for this example, you see 2p2. 2 is even, right? So you might say, well, it's an even number, therefore it is diamagnetic. But as you can see by inspection,